Hi, everyone. My name is Josua Aponte Serrano. I'm a postdoctoral fellow at the National Institute of Allergies and Infectious Diseases, NIAID. And I will be talking today about chemotaxis, the directed movement of cells guided by soluble chemical signals, and how we can use CompuCell to address some of the interesting and outstanding questions regarding this type of cell movement. I should also mention that my current project at NIAID, it's also very much related to how cells can sense differential signals and how can this induce, let's say, cell movement in a particular direction. So even though I'm currently at a different place now, chemotaxis is and using spots or the type of modeling that we use using CompuCell is something that very much is present in is still present in my current research. So this is a little overview of what I will be talking about today. We will talk about the type of cell movements and directed cell movements. We're going to talk about a little bit more in detail about what chemotaxis is. We're going to talk a little bit about what are outstanding issues regarding how we understand the molecular basis and the physiological basis of chemotaxis. And how we can use CompuCell to model chemotaxis from in incrementally complex approach, starting from a very simple model of chemotaxis and then adding more complexity to it until we can until at the end we will look at an existing example of a neutrophil really chasing a bacterium and how it's been implemented in CompuCell. I want to remind everyone, that the meeting is being live streamed and recorded, and it will be publicly available later on YouTube. So there are eukaryotic cells. There are some type of eukaryotic cells that can alter their end response in their behavior as response to gradients or spatial variations of a specific type of signal in their environment. And this is particularly important in there's areas of biology where this is particularly important, specifically during development. Cells need to move in a particular direction according to the development plan. It's also true in immunology, where cells need to move in the direction, let's say, of the infection site, right? They have to be able to find the infection site and then move in the direction of the pathogen. And it's also true for in cancer cells and metastasis cells do move following certain signals. And this type of directed movement, as opposed to, let's say, random cellular movement, can be directed by different factors, right? Some of them of particular interest can be because of the differential because of differential addition to a substrate. Let's say there's more addition molecules on one side versus the other, so cells can sort of move either in either direction, guided by this differential presence of addition molecules. It's also true about light. It's also true with temperature. And again, in the particular case of chemotaxis, we refer to chemotaxis as the movement of cells guided by a soluble molecule in the extracellular environment. The most classic example of chemotaxis is that of dictyostelium. It's basically an amoeba that moves when in different stages of development, it will move guided by different type of signals. And one of those classic type of movement is when the amoeba is moving to the source of cyclic AMP. There is a video here that I'll have to show using YouTube because so the pipette is a source of cyclic AMP, and then we can see DICT moving in the direction of that signal. I do have to mention that DICT is probably one of the best. DICT is a classical model of to study cell chemotaxis because of the tractability of the intracellular signaling pathways. But some of these pathways are relatively conserved, and by studying DICT, we can gain some understanding of other like more complex cell types, such as cells of the immune system, neutrophils, macrophages, can also differentiate gradients of signals and then polarize and move in that direction. There's another interesting aspect is of chemotaxis is that it can produce this set of patterns of movement when we look at cells aggregation of in this case dictotelium cells and there's a lot of modeling that's been devoted to this type of patterning that arises from directed movement, but this is not what we are going to particularly look at the moment, where we will look at the how we can model single cell movement using CompuCell. I do have to mention as well that chemotaxis is a very complex process that incorporates many stages, right? It incorporates the detection of the molecule of the signaling molecule, right? And then the transduction of that molecule into a intracellular signal that can then induce some sort of polarization in the cell, some sort of differentiation between, let's say, the front and the back of the cell that allows the cell to move in that direction. So these are all different processes, and they are studied pretty independently. But at the end of the day, we can combine them. We will not, at least at this stage, we will not try to combine a lot of this stuff. But next week, when you guys talk about network modeling, you can start thinking about, okay, how we could potentially couple this type of network modeling that is used to represent the intracellular processing with the CompuCell POTS approach, where we model changing cell morphologies. So some of the outstanding issues and some of the ideas that we need to take into consideration when we want to model chemotaxis are related to, again, some of these different processes that I was talking about. So in terms of the signaling molecule, what is the biochemistry of the molecule? Is it freely diffusing? It's actually really bound to an extracellular matrix. Whether the cell movement itself has any effect on the differential on the spatial gradient of this molecule, whether when the cell moves, it creates some sort of flow that disrupts its gradient. This might be more of interest on the biophysical side than on the, let's say, more molecular or cellular side. But those are interesting questions that you could also ask. Another, in terms of the signal reception and transduction, so interesting questions are how are the cellular cell surface receptors distributed over the cell, and whether these change over time, and how this changes over time can how the cell manages to, let's say average these changes over time such that it maintains the right polarization. That is a question we are currently working on and here at NIAID. in terms of when the cell extends filipodia or lamellopodia, there are changes in the distribution of cells, cell surface receptors, and hence there are local variations in how the cell perceives the signal. So one of the questions we are trying to answer here is, how is the cell polarization maintained despite these local changes associated with membrane extensions? Other questions have to do with the intracellular processing of this gradient. So how is the signal process inside? What are the molecular? What is the molecular pathway leading to this processing? Whether there is an amplification, and we know this because cells can move in very shallow gradients. But to move in those, being able to move in those very shallow gradients, cells need mechanisms that turn or convert that shallow difference into a steeper difference inside the cell in terms of distribution of signaling molecules. Yeah, there's some of these questions, as I mentioned, most, if not all of these questions, we can use CompuCell to answer. The Chemotaxis plugin is fairly elaborate and allow us, and we can address some of these questions, especially in combination with other capabilities in CompuCell. But of course, there's limitations in terms of, like, there's other questions and it might not be appropriate to CompuCell, might not be an appropriate platform to address, but for all of them, we can use CompuCell to address some of those. So now let's get into how we can think in terms of, like, modeling, right? Not some independent of CompuCell, but like how we can think about how does a mathematical model of chemotaxis look like. So as we've talked about, as it's been discussed before, we can think as this diffuse signaling molecule as a chemical field that is distributed over space with a uniform diffusion rate, and importantly, for the moment, that cells do not affect this field, such that the cell movement basically occurs on a uniform and unchanging chemical field. And then we assume further that the field exerts a local force on the cell membrane that is proportional to the gradient, or the difference, let's say, between one spot in space and the other. And then that force is going to be proportional to this lambda chemotaxis term, or this proportionality term that we call lambda chemotaxis, that allows to, of course, proportionally or scale the force relative to the other forces that might also be exerting over the cell. So this is a very simple model of chemotaxis, and we will see more complicated models down the road. But this one in particular can have, if we think about the limiting cases, this can have unintended consequences. Specifically, that when the gradients become very, very steep, that cells will move infinitely fast. Again, that cells do not cause advection of the signal. The signal does not move as the cell moves. And that the cell is not removing or affecting the signal, the background signal. So basically, it's as if the cell was moving on a background that is not affected by it, right? Let me make sure. Yeah. Okay. So now when we implement this in CompuCell, the idea would be, or the idea of how chemotaxis is implemented in CompuCell is that the Hamiltonian, right, or the probability of a pixel change happening is gonna be proportional to the value of the chemical field the pixel is being moved to, right? Let's assume that there is a chemical gradient that it's moving in this direction, right? So you can see that the value is 3 here, 2 here, 1 here, 0 here, right? And then the way chemotaxis is implemented more like abstractly is that the probability of a pixel exchange happening is proportional to the change on the concentration, right? So so a movement, let's say a copy from this pixel to this pixel is less likely than a copy from this pixel to this pixel, right? And again, the probability will depend on what the change in that the concentration of this chemical gradient is, right? So the blue arrows here represent all the possible or the favorable copies based on this chemotaxis term, right? And again, whether the cell moves in that direction or not, it's dependent not just on the chemotaxis term. We have other terms as well, right? We might have some volume constraint, surface constraint, and those need to be balanced in a way that allows the cell to move. Because if one of the terms is unbalanced, then the cell might not move because it has to satisfy other constraints. But that's where equilibrate. That's where the lambda chemotaxis or the proportionality terms come into play and allow you to basically calibrate the model in such a way that each term has similar contributions. So so we have we will, or I'll show how to implement this very simple chemotaxis term, but just so we can get as a first view into it. Once we implement chemotaxis using the CC3D ML, what we get is a piece of code, very simple, that allow us to specify what the chemical field the cell is going to move to is, what the cell that moves, the cell type that moves, because for example, we could have two cell types, one that moves up the gradient and one that it doesn't, or one that moves up the gradient and one that moves in the opposite direction. So we can specify that by specifying the type of the cell that moves, that this chemotaxis term is applied to. We specify also the lambda, and this chemotax towards tells you whether what type of cell the cell can move to or over based on the gradient, right? We'll look a little bit at that right now. So let's just start with a simple simulation. For reference, I've uploaded all of these examples to the module drive. You can see, and you'll find them labeled 0.3, 0.7. You can see the final product of that one. So let's just come to it, and let's create a new project. And then it says that we're going to create, let's call it chemotaxis simple. We're going to use Python and XML because at this point, we're just going to specify everything using the XML. And then we're going to specify a 200 by 200 by 1 lattice with periodic conditions in X and Y, and no flux in Z. we are gonna use a rectangular slab to create our cells. This is the blood. Yeah, I can definitely do that. 1 second. Because I'm just using that one to follow the instructions because I don't remember them myself, but I will do it in a second. Just give me 1 second. I'm gonna create a cell type called cell. I'm gonna create a field called field. I'm gonna use a diffusion solver FE, and then I'm gonna let's see what are the I'm trying to split the windows. Let me see if I can split them just here. Let me finish this one, and for the next example, I'll make sure to split the windows. But I'll enable contact, the volume, and chemotaxis. Contact, volume, and chemotaxis. Then when I enable chemotaxis, it shows it. This is probably the first time you've seen this window. It allows you to specify the chemotaxis properties using the GUI. We are going to just 1 second. We are going to just to make sure that I get the parameters right. Okay. So we are going to specify the lambda chemotaxis to be 500. The field and the cell type. So the cell type, cell moves towards field with a lambda chemotaxis of 500, and it chemotax towards cells medium. So it basically moves through the medium guided by the field. And then I add entry. Oh, sorry. Okay. So as I said, we're just gonna use the XML. So we've you've seen this before. We created for now we're just gonna use the XML. So we created a the simulation domain, and what we will do now is that we have the contact energies, and then we can see our chemotaxis plugin specified here. And then what we will do is that we are gonna create a gradient of the field. If I simulate this, I have to specify how the field looks like, and I'm sure you guys did this already. There's ways there's ways to do this that are more or less complicated, but we don't want any secretion, so we don't want the cell to secrete anything. And then what we want is a global diffusion coefficient of 0.1 and a decay constant 0. And then what we want is what we want is the value of the field to be, let's say, 1, and by 1 we mean whatever. We can mean 1 nanomolar, 1 micromolar, but we want the value to be 1 at the minimum of X and 0 at the maximum of X. And then in the Y direction, we want it to be periodic. And so if I do this, what will happen is that this the simulation will start with a value of 1 of the chemical field and on one side of the simulation domain and 0 on the next. And then I have to wait for it to sort of equilibrate before I can see chemotaxis working properly. So to avoid that, I can specify an initial constant expression, an initial concentration of the field at every particular position. And for that, I can specify, I have the mathematical way of, I know what the gradient looks like at equilibrium. So basically, so I changed, no, so I the global diffusion coefficient I set to 0.1, and then the decay constant I set to 0, basically. The global, but I eliminated the secretion term because I did not want the cell to produce any of the chemical, and that just comes with the original. When I load the diffusion solver, those are the initial values, and I'm just going through and changing the original values. Can you show initial values? Oh, so the initial value is this, and it's because right, I want it to be 1 where X is 0 and 0 where X is 200, basically. So why? So because what I'm trying to do, and this goes back to the chemical fields, not so much about chemotaxis, but what I'm trying to do is I'm trying to create a chemical field that has a value of 1 on one side of my simulation domain and 0 on the other side, and it's linear between between those two simulation domains, right? Or changes linearly between the edges of my simulation domain. So this is basically what I'm doing here. It's just creating it's literally creating a linear gradient between one side of my simulation domain and the next. So, and again, I use the uniform, I specified the uniform initializer here. It might be better to specify use the blob initializer. So, and this is good practice, good example, because you can change things on the fly. You don't need, let's say you initialize a simulation and then you notice, oh, I did not want to use the uniform initializer. I wanted to actually use the blob initializer. I could come back here, delete it, and then go to my CC3D ML, and I can go to steppables and I can add the blob initializer instead. So if you at some point made a mistake, you don't have to, let's say, go back and redo everything. You can just change things on the fly. So I'm gonna initialize a cell that is basically on one side of my simulation domain. It has a radius of 3, 0. So this is basically initializing one single cell. I'm using the blob initializer because I specify the radius of the cell to be 3. Width would be how much space are between two cells. So I'm specifying the width to be bigger than the radius of my cell such that I can initialize just one single cell. Let me see. The last thing I need to specify is the volume, because I don't want my cell to disappear. And that should be all. Let me see if there's any questions. Okay, good. So with that, I should be able to simulate, let's see. So yeah, this is not exactly what I wanted because I wanted it to be 200 by 100. But I mean, this is fine. If we look at the field, we can see that the field is it's a linear field that goes from the value of 1 on one edge to 0 at the other. I mean, if I want to, again, as I said, like if we want to correct this by changing the simulation domain, all I need to do is to change this here and restart my simulation. And you can see this is actually what I wanted to do in terms of what I wanted my simulation to look like. So you can see the field, I can see my cell, I initialize it on one edge, and I specify the chemotaxis. So if I run it, so I can see how my cell is moving in the direction of the gradient, right? Now we can do a little bit more fun stuff. We can let's use the Python script to see whether we can plot the position of the cell as it moves. So I come to my steppable Python file, and then all I need to do is to use this on the start function. I can set up a plot window. Let's call it position versus time. And then the series or the plot series, let's call it position. Let's make it dots. That's fine. And then all I need to do is to so basically record the position of the cell at certain frequency and add it to the plot. So I just have one cell, so I can do this safely. And then I can add a data point. And again, as we saw, my cell is moving just on the X direction. I can also add the Y direction, but movement on the Y direction is just due to random fluctuations because it's not directed by anything else. So I'm just gonna plot the position on the X or the center of mass of the cell on the X direction. Cell attributes, center of mass. And the one I need is in the X direction. Okay, I'm gonna stop here to let everyone catch up for a second. Right. So for example, if you were interested in looking at the correlation between the temperature, right? That POTS term that we call temperature, and how it affects the directed and the random movement, then you could potentially plot also the movement in the y direction, and then or the position in the y direction, and look at how that changes as you play with some of these parameters. So, okay, let's come back here. Let's save it. Now I have a plot that shows the position versus time, the cell. And then, of course, there is a lot of noise. And again, this noise is associated with this random membrane fluctuations. But you can see that as the cell moves up the gradient, the position changes in my plot as well. Okay, I want to ask someone to I wanna ask someone who's already caught up with the code to run 2 or 3 simulations and then change this, come back to the XML. I'm gonna give you a couple of minutes, come back to the XML, change this lambda chemotaxis value here, let's say by a factor of 10, put it like turn it into 50 or turn it into 5,000, run it and tell me what you see. You can type it in the chat. Right. Right. And you could potentially analyze it too, right? And we'll see a little bit of that. How it's chemotaxis affected by some of the parameters. But yes, it should in principle have it depends, right? There's a range in which it has a linear effect on the speed. But as Gilberto was talking about earlier, there is a limit to how fast can cells in CompuSol, just due to the Metropolis algorithm, where it can move just 1 pixel per Monte Carlo step. So you reach eventually that limit. Cool. Maybe we can change it here manually too. And let's see. We can pause. We can come here. Let's turn it into 5,000. All right, that's not what I wanted. And play it. So you can see now I change it here in my model editor, and you can see very clearly how the speed increased. And then let's come back and turn it into 50. Then now the cell is barely moving. Another question I have for people: what happens now if I turn this, let's say, into minus 500? What would you? Yeah, exactly that. Favor movement would be opposite to the gradient. So instead of going up the gradient, the cell will go down the gradient. Let's make it faster. So you can see that now the cell is moving in the opposite direction. Okay. Okay. I will so there is an example, there is a copy of this code in the modules file. If you want if you want, if you need to reference the code, I would suggest you put it side by side and look at your code and compare it to this example. Okay. There's a couple of other examples I want to walk through, so I will continue. But again, we'll have time for discussion at the end. And again, if you have further questions, there's the example code. Yeah, so this is what we did. This is for reference for those when you want to look at the code by yourself. So a very interesting example that I like showing is how cells can move in a self-constructed gradient, and this is a very good model of bacterial movement. You'll see because it will show some typical movement where bacterial movement where you see some sort of like persistent in one direction, then due to membrane fluctuations you'll see that the cell moves changes direction and then persists for some time, and then it continues in that, and then it continues for a little bit and then it changes direction again. Okay. Again, there is a copy of this example in the demos. Again, we will the convenience of this example and the previous example is basically that we can specify all of the example using just the XML. So we'll come back here. Let's close this project. Sorry, that's not what I want to do. Let's close this project and let's create a new project. Let's call it self-gradient. Again, we need the Python and the XML, though we're not going to use the Python file. And then we want 200 by 56 is fine. And then we want periodic boundary conditions on X and Y, no flux and Z. And then again, we will initialize a cell called cell. That's not very creative, but it's convenient. And we're gonna specify the field called field. And then we want volume, contact. We want chemotaxis. I'm gonna go back because I'm gonna use the blob initializer, not the rectangular slab. Okay. And then again here, the cell, we're gonna specify at 200 lambda, chemotax towards medium at entry. Let me check the chat. sorry if the example says different instructions. I'm sorry. At the end of the day, the size of the simulation domain, I don't think it matters much. It's the bigger it's just gonna be a little bit. It's gonna show a little bit. It's gonna show better. So we're gonna come to the XML, and so here we have again our simulation domain properties. We have our type of cells. We have our volume parameter or a volume constraint. We have our contact energies. And we have our chemotaxis term, again, or a chemotaxis plugin. We won't have to change this for now. But what we need to do is that we need to, so we want to basically, we basically want to create a field that does not, basically that diffuses very slowly, right? And or doesn't diffuse at all. And then it decays only inside the cell. And this decay inside the cell is gonna be a proxy for cell uptake. It's basically what we're gonna be simulating here is a cell basically eating up the field and then moving in the direction of higher concentration. So we can think of it as we have a nutrient that is basically that it doesn't move or diffuses quickly enough, and then that the cell, as it eats it, it needs to move to find more source of this nutrient. So we can, there's multiple ways of doing this. This is just to avoid complications, this is just a proxy of that. Again, we don't want the cell to secrete any, so we're gonna get rid of that secretion data. And then we want the field to be periodic both on the Y and on the X and Y axis. Okay. And then we're gonna use the initial concentration expression to set the maximum value of this field to be 1. Again, 1 just because it's a arbitrary number, but it allows you to convert easily between, let's say, units in compute cell versus actual biological units. And then let's create a cell in the center of the simulation domain. So we do this by specifying, again, doing the same. We specify a radius of 5 for the cell and a width of 7. That's fine. So the radius of the cell is bigger than the separation between two different cells. That should do it. Let's just make sure that the code is all right. Okay, this should work. Let's come here and open the simulation. Again, if you guys need me to stop at some point, please let me know in the chat. So I have that cell, single cell in the middle. And if I look at the field is uniformly distributed in space. And you can see if you zoom in that there is no field inside the cell. I didn't initialize any inside the cell, and they say it's uptaking the field. And then if I start simulating it, you can see how the cell is moving. So you can see that it has a persistent movement, a persistent direction of movement for some time, and then it changes direction, and these changes of direction are only due to the membrane fluctuations. And you can see how the cell sort of like, in this particular case, because the space is so big, the cell has a lot of space to move. But if we were to, what we'll do next, add more cells, you can, and then start seeing how cell starts avoiding, let's say, space that it's depleted of the nutrient, right? And again, some of the interesting stuff that we can look at here, or we can quantify and compare to experimental data. Again, the persistence time in movement in a particular direction. We can also look at the speed and so on. Okay, so I'm gonna stop the simulation, and instead of having one cell at the center, I'm gonna initialize 2 cells or 3 cells. In this case, I'm gonna have a radius of 25 and a gap of 15. So this is an interesting question James is making, right? Like, so if I want to plot this, the speed, how would I do it, right? So taking into consideration that there is this persistent time, right, and persistent direction, right? Like if I want to calculate the speed, I need to be able that I need to be able to measure the distance between cells to be or the frequency with which I measured the distance or between, let's say, position 1 and position 2 of the cell needs to be shorter than the persistent, that the time that it takes for the cell to move or to change the persistent direction, right? Because otherwise my quantification of the velocity might be skewed. Okay, so let's come back here. 25, 15, 7. Let's see if we can initialize 3 different cells. There you go. So you can see, for example, how cells are avoiding areas depleted of this nutrients. This one gets stuck in a low concentration area, and basically when it's in that low concentration area, it's basically tumbling around, randomly moving until it reaches an area rich in nutrients, and then it continues moving, right? So in this example, cells are not producing any chemicals, really. If anything, they're consuming it. And the way to implement it by proxy is to setting the decay coefficient inside the cell to be, let's say, if anything, higher than the global decay coefficient, such that the cells are consuming from the environment, right? So it's, for example, this cell ran into this area of low, and you can see how it's moved away from it. Same here. And again, when they get stuck in areas of low concentration, they basically randomly move until they find an area where there's some nutrient left and move up that direction. Okay. This is a very, I find it like a very cool simulation and really easy to implement. Okay. Again, as I said, if you want to compare your code to the code that we wrote here, there is a you can find the demo in the demos folder, and you guys can compare your code to this code to make sure that it's working properly. Okay, let's continue. Let's continue working on it. Yep. So CompuCell allows you so far we've specified the chemotaxis only using the XML specification, but there are options to specify the chemotaxis or the chemotaxis plugin using the Python file, the Python stepables file. And the advantage about this is that gives you much more flexibility in terms of how to modify this value, right? Let's say you want, as we will see, let's say you want the lambda chemotaxis to change after a certain time. Let's say you want the cell to move up the gradient for some time and then down the gradient for another time, right? So in that case, you would need to use the Python specification file rather than the XML, which is fixed. And the way to do it is that we load this plugin in the Python file. We set the lambda chemotaxis, and then we can modify it on the fly. So we're gonna use the same code that we use for the simple chemotaxis, and then what we're gonna do is that we're gonna change the lambda chemotaxis as the cell move in one direction and the other. So we would start with a chemotaxis of 500, and then we will change it by a factor of 1.2 every 1,000 Monte Carlo steps, or every time the cell reaches one edge of this simulation, right? And as we explained earlier, the sign is gonna change the direction of movement, right? Okay, so to do that, let's close this project. Let's open again the same we had before, the simple chemotaxis. I'm just gonna save it as, I want a different name. Let's call it Python specification. That has a different name in the demos. Okay. So to do this, we still need this chemotaxis plugin specified in our XML, but we cannot have any information specified inside of it, because if we have the specification on XML, we cannot override it using Python. So we're just gonna comment it out. So we're basically specifying, we're loading the chemotaxis plugin using the XML, but we are not providing any information. So this information we'll have to provide using the Python step hours file. Okay, we will leave everything else the same. Remember that what this code does is that establishes, and this is discussed from previous sections, establishes a linear gradient that goes from 1 to 0 on one simulation domain to the other one, right? So if I run this simulation now, it basically shouldn't do anything, in the sense that because I have I have not specified any information about the chemotaxis. So it's just gonna be, sorry, that's the error. I commented out something here that I shouldn't have. Everything all I changed was this. Let me see. 1 second. Okay, yeah, I need this, but what I don't need is the actual information inside. There you go. So so when I was talking about how we need to comment out the information inside the chemotaxis plugin in the XML, all you need to comment out is the specification of the cell type with the lambda. But if you comment out the specific field that the chemotaxis term is going to apply to, then you get a segmentation error. That's what it came from. So as I mentioned, if I plot this, it's not doing anything. So if anything, it's moving randomly because I haven't specified anything about the chemotaxis. Okay. To do that, I come back to the Python file. And then what I can do is, so the way it works is that I have to load the right, 1 second. Yeah, so I need to load the plugin and add it to a specific cell, right? So this allows me even more flexibility because let's say I want some of my cells to, even on the same type, right? I want some of my cells to migrate and some of them I do not. So I specify the chemotaxis plugin per cell specifically. So let's see where chemotaxis by cell ID, right? So make sure it says make sure the chemotaxis plugin is loaded. That was back on the XML. And then for I am defining it for individual cell. For the moment, I just have one cell, so I can iterate over my list of cells, which is just one. And then I need the field name to match the field that I specified in the XML. Did I specify? No, it's with capital F. And then my lambda chemotaxis, I'm gonna set it to, let's set it first to 5,000. And then towards vector types, so the type numbers are specified here, right? So I just wanted to chemotax towards medium. Okay. And notice that I did this in my star function. Let's play the simulation again. And then now we can see that the cell is actually moving up the gradient because I've specified the chemotaxis using the Python interface. And let's just add a line of code that is gonna change the chemotaxis, the sign of the chemotaxis term when and increases it when the cell reaches the edge of the simulation, right? So what I need to do is okay. This is in the code I sent you. It's a little bit complicated, but we can say okay. Right. Let's do it this way. Or let's just do it whenever it reaches the edge of the simulation. So the first thing we're gonna do is that we're gonna get again the chemotaxis plugin for the cell. So again, I'm getting, no, it's not add, it's get the chemotaxis plugin for the cell. And if this chemotaxis plugin is loaded, then we want the value of that lambda, and the way we get it is get lambda. So now LA is the value of the lambda chemotaxis loaded into the cell. And now if lambda is because we're gonna change it between positive and negative, right? If lambda is negative and the cell is less than 20 pixels away from the edge. That's basically what I'm doing here. And make sure that I have that right. Right. Okay, this is right. Or the opposite, if it's going in the opposite direction and the cell is less than 20 pixels away from the other side. This is the left side. Then, so basically what I'm saying here is if it's moving on the left direction and it's 20 pixels away from the edge at the left direction, or it's moving on the right direction and it's 20 pixels or closer to the right direction, to the right simulation edge, then I want the lambda chemotaxis to increase by 1.5 and change direction. And then I can use this to set the lambda chemotaxis. Okay. The code in the example is a little bit more complicated because it adds another condition. It adds, if the cell hasn't reached the edge by 1,000 steps, then change it anyway, right? And that's in the case we want to start with a very low lambda chemotaxis. Let's see if this works. Syntax error. Sorry. I typed a lot of stuff. Okay. Yeah, thank you. Okay. So now the cell is moving from one side of the simulation domain. Where is the cell? It's almost reaching the edge. So there was a dim that X, sorry. Right. Right. Let's run it again. The cell is almost there. And you can see how it changed direction and it reached one side of the simulation domain. And now it's moving slightly faster. And it should change again direction. There you go, change direction again. So this is just an example of how you can use Python to, it gives you a little bit more flexibility to control the chemotaxis term that the XML doesn't, because the XML is static, right? So once you define the XML, that is static for the whole simulation. Whereas in the Python step hours, you have a little bit more control of how these values are changed through the simulation. And you can see again, it's bounce back. And you can see that every time it's a little bit faster, okay? I'm not gonna let it run for much faster because there's a couple of other examples that I wanna walk through. No, we're running out of time. Right, so the simulation, we could potentially plot we could plot the velocity of the cell as a function of the lambda chemotaxis. All we need to do is to record the position. We need to record the time that it takes between changing directions. And then when it changes directions, we can divide that by the time it took and then plot it. And then it sort of gives you a sense of and that is in the code I provided. It gives you a sense of how the lambda chemotaxis depend, or the velocity depends on this lambda chemotaxis. I'm gonna show it here. So you can see if we were to add that plot, I just have 10 minutes. So, and I wanna at least walk through the other examples. But you can see that it changes, the speed changes as the chemotaxis, the lambda chemotaxis increases. And as we discussed earlier, it has a saturation where it won't move faster. And in this particular case is of a quarter of a pixel per Monte Carlo step. And again, the code that I provided does adds the velocity and plots it as a function of time. And you can use this code to test not only the you can. Yeah, so sorry, that was a mistake. Yeah, it was deemed that X. I forgot to add the X. So to specify that is the dimension on the X direction. But yeah, you can use these code to test how velocity depends on other parameters, not just lambda. You can, for example, set a fixed lambda and then increase the cell volume. Let's do it. Let's increase, because the other examples I'm not going to be able to go through the code, but I'm just going to walk you through. So let's just ask for fun, and this is not in the code that I provided. Instead of changing lambda, let's set the lambda to a relatively high number, so we don't have to wait that much for the cell to reach the. And then instead of changing the lambda, which is what I'm doing here, let's increase the cell target volume. Sorry, that's all code. That's all. Yeah, 1 second. So properties, change target volume. Cell target volume, let's increase it by a factor of 1 of 2. So that's a lot, but maybe 1.5. And let's increase this lambda term so it moves actually faster. So in this is not in the examples that none of the code that I showed, but this is an example of how we can look at how the other parameters might affect cell movement, and in this case, cell size. And my computer, I think it's frozen. 1 second. Do you guys still hear me well?
Yeah, the stream is fine.
Okay, because my computer, I'm gonna have to close it.
There's a little bit of lag on your screen share, but your audio and your video are fine.
Okay, good. So, as I said, I'm making the cell move faster because I wanted to reach the edge. But then every time it reaches the edge, instead of changing the, instead of changing, I need to change lambda. That was very smart on my side. But let's just change the sign of lambda and not the value. Sorry about that. Remember, because I want the cell to be able to change direction, but I do not want to increase my lambda. What I want to increase is the cell volume. Okay, let's actually make this cell move faster. And let's increase the target volume faster, just for the sake of the example. Good. Well, to do that, of course, the same stuff that I've been discussing, I've specified the volume constraint on the XML that won't work. I need to do it in Python to be able to change it. So in the start function, in the same, where I set the chemotaxis plugin for the cell, I also need to set the target volume for this and the lambda volume. So the initial was 50. Sorry about that. And then the cell lambda volume was 2. This is good because, again, it reminds us that if we specify anything on the XML, we won't be able to change it on the file on Python. So I have to come back and uncomment that out, comment the information on the volume constraint in the XML, and then specify it on Python, and then now that allows me to change it. So it's moving relatively fast, and this is just for the sake of the example. But you can see that now, as it reached the edge, it increased in size. And remember, when it reaches the edge, all I'm changing is the direction of the lambda. And again, if we were plotting, we're not, but if we were plotting the velocity as a function of the size, we could potentially see what the relationship is there. But if anything, by the simulation, I would say that it's moving a little bit slower. Yeah. So the same lambda will probably make the cell move slower, whether the cell is bigger or smaller. Or it shouldn't. I'm not 100% sure that there should be a correlation, but it looks like that might be the case. Okay, so yeah, those are all interesting stuff that we can explore using the Chemotaxis plugin. What I'm gonna do in the next couple of examples, because we're about time, is that I'm gonna show what else you could potentially do, and the examples are up in the demos. And then if you guys have further questions, we can discuss them later. So as I mentioned earlier, one of the unintended consequences of this type of linear chemotaxis term that we're applying is that the cell will move infinitely fast if the gradients are sufficiently steep. And that's not usually how cell responds. Usually where cells are exposed to very steep gradients will not respond at all. So we have a way of implementing this in CompuCell by saturating this chemotaxis term. And we do it. So instead of, for example, if we have instead of having a linear gradient, we have an exponentially decaying gradient. Our cell with this linear term will move, let's say, infinitely fast as it approaches as the steep of the gradient increases. Again, this is not biologically realistic, so we can sort of like have a more sort of uniform response, which is probably what cells do, by saturating this chemotaxis term. And I'm gonna show just the code as an example. One second. The chemotaxis saturation. So we, as I specified, we load the plugin, the chemotaxis plugin in the Python file, and then here we get the value of the field at the center of mass of the cell, and then we divide our lambda by this value. And that way we saturate that lambda chemotaxis term in a way that allows the cell to respond more appropriately in the face of very steep gradients. Okay. And lastly, there is a demo, and I've always really wanted to get to this point. We always run out of time. But there is this interesting demo that comes with CompuCell that simulates a neutrophil macrophage. I will walk through. Yeah, I will walk through the code and maybe explore one or two parameters. But this is. So this very interesting model that simulates a neutrophil chasing bacteria around red blood cells. So this is I've uploaded the code for this simulation, but this simulation comes already as a demo with your CompuCell. And it allows, thinking about this, it allows us to, so for example, how we go from microscopy images to simulations in terms of what are the, or how do we represent the biology using literal code, or how we abstract a model from, let's say, some type of microscopy data and then turn that into a simulation. These are some of the stuff that we need to like take into consideration. For example, when we look at the image, we notice that the bacteria seems to be fleeing the neutrophil, but it doesn't seem to be actively fleeing. It seems to be more so like pushed away, maybe. That there is a particular shape that the neutrophil has, that it's very oval. That it sort of like knows where the bacteria is and sort of like follows it. And that the velocity of the movement doesn't seem to be changing. At some point, it seems to eat the bacteria altogether. Or that might be a little bit more difficult or sophisticated to implement in CompuCell, but it can be done. And that we have this red blood cells that are pretty rounded, and they're, if anything, they do not stick to each other. The neutrophil do not stick to them, and they're just passively there, right? So and then we come to think about, okay, what are the properties that I have to assign to my cells for this simulation to be able to implement such a simulation. So we we know that the bacterium has to have a volume and a surface, maybe some motility, maybe some adhesion, that the neutrophil, or at least it has some interaction with its surrounding media, that the neutrophil also has some volume and surface, that it definitely moves, and again, it interacts with its surrounding in some particular way, doesn't stick to, let's say, the environment. Same with the red blood cells. We can assume that this bacteria is secreting some type of signal that the neutrophil is able to detect, and that signal diffuses away from the bacteria, and that this signal induces the movement of the neutrophil in the direction of the bacteria. So let's just run the simulation to see how it looks like. You find it in demos, models, bacterium, macrophage, periodic, but I also uploaded it to the demos file. And you can see we have in yellow, we have our neutrophils. In blue, we have our bacteria. And then in red, we have our red blood cells. You can see in this particular simulation, there seems to be a couple of neutrophils that have trouble moving. We can go back to see what some of the parameters to see what are the specific parameters controlling the simulation. So all of it again is specified in the XML. So here we specify we specify the volume constraints, the surface constraints. Maybe if we want we could potentially get rid of the surface constraints and see, for example, whether that affects the movement. Yeah. Yeah, so it doesn't seem to have significant effect on what the cells look like. We can ask then a couple of questions. So what happens, how the detection depends on the diffusion of the signal. Let's make the diffusion 10 times faster, the diffusion constant 10 times faster, and we see that neutrophils, if anything, are better at detecting where the bacteria is, right? And then, yeah, so we could potentially change how many bacteria we have relative to the neutrophils, see how the neutrophils decide which ones to go after. So what happens if the neutrophil, this one's easy to implement, absorbs the chemical field? So we saw this. So we saw that we did this in the self-created gradient, where we had the field decay inside a particular cell. Let me see what the specific syntax is. It's gonna be in diffusion data, and it's gonna be decay coefficient by cell type equals macrophage, and then let's set it to, this is a global, let's set it to 10 times this value. And now see that yeah, if anything, I feel like it has a little bit more trouble finding the cells. Yeah, that's for sure. Yeah. And there's a lot of other questions that you can, and this one is, I'm going to, as an exercise, fun exercise for everyone, how we could simulate the neutrophil actually eating the bacteria. There's a couple examples for if they're in contact, you can decrease the target volume of the bacteria. Depending, you can, for example, because in the movie, it doesn't seem like it actually killed. It's not like the bacteria just disappears. It's more so that it's engulfed by the neutrophil. You could potentially change the contact energy between the neutrophil and the bacterium after certain conditions met. And yeah, I'm gonna stop here. But if you guys have any other questions, please, if you guys have any questions, feel free to put them forward now, or you can email me. I'm gonna put my email in the chat. Feel free to email me if you have any further questions about these simulations or CompuSol or anything else. And thank you so much for your attention.